Okay, buenos dias, camaradas. I'm all the way from Mexico. So the title of this talk is DirectX, Direct Way to Windows Kernel, but in fact it's not about DirectX. It's about poor quality of video drivers in Microsoft Windows. So let's start with the agenda. So I'm going to talk about WDDM model, then basically attack surfaces, like reverse engineering, fuzzing approaches. I'm going to show live demo. I will try to blue screen this computer. If it doesn't work, I will show video demo. And I'm going to also talk about some interesting attack vectors, more complicated than escape. So before Windows Vista, it was XDM, and it was kind of a lot of functionality has to be made by manufacturers of video drivers. So there were a lot of mass, and at Windows Vista, Microsoft decided like make a new model that will be way easier to program. And DirectX, basically, it's a couple of kernel drivers in Windows. Main is dxgkernel.sys. Also, there is some driver that works on scheduling and other various stuff that's related to video processing. So actually, if we talk about video drivers, there are two parts, user mode drivers and kernel mode drivers. So in Windows operating system, there is a DLL GDI 32.dll, so basically graphic interface. And user mode driver, or for example, NVIDIA or ATI or Intel, it works like a proxy between kernel, which actually dxgkernel.sys, and GDI. And it intersects some like calls, make some magic and stuff like that. So there are like video like works with abstractions like handles, context, surfaces. For example, when you program in the user mode, you like operate with like handles with some entities, and all magic happens in kernel. So basically that like a diagram how it works. So on top there is some application. There is also Direct3D runtime of Windows, OpenGL, and GDI 32.dll. It's like gateway. So before going to GDI 32, user mode driver does some processing, and then to GDI, and then to kernel. And in the end, it goes to kernel mode driver. The only talk that before this talk was made regarding this area, it was made by Ilya Van Sprundel a year ago at Black Hat, and basically he showed like attack vectors, some system calls that basically you can fuzz and get some results. And like arguments of these functions, there are buffers, sizes. So this table shows interesting arguments for fuzz. For example, if we talk about escape function, which is a main attack surface, because it's kind of ISCTL, but for video kernel drivers. So there are buffer, which is vendor specific, there is size. Other system calls that are not very, how to say, complicated. Like query adapter info, basically it's just a function that asks like for some information about video card, and in fact I haven't found any interesting code, any like vulnerabilities. So talking about like how it the flow actually is kind of complicated. There are a lot of system calls. So first of all, it starts that user mode code has to get device. the thing is that on a laptop or even on a PC, there can be two video cards. Like one integrated, for example, Intel, and one is NVIDIA or ATI. So in fact, when you fuzz, you can like fuzz two video cards. So when you call create device, you basically create like handle. In kernel, there is a big structure that represents the device. Then you create context, and then you create resources. It's in user mode, it's all handles. But in fact, via like using some system calls, you operate with some structures, with some memory in kernel. So after we get context, like device context, we can make some rendering, for example. And rendering is a very complicated thing. So we just like invoke system call render, like DXGK render, and in kernel mode there are a lot of flows between DXG kernel runtime and the kernel mode driver of vendor-specific card like ATI, Intel, or NVIDIA. So, like this is a typical like flow chart. What's that? It's okay? ¿Todo bien? Okay. So, when it's made, if it's made in Latvia, I don't drink it. It has to be made in Russia, okay?
No, it's made in Russia.
In Russia?
Yeah.
You brought it all the way?
Yeah, all the way.
Mi camarada.
На здоровье.
Good. So, where are my slides, goddammit? ¿Qué pasó? I need help. Ayuda, ayuda. No, seriously. Yeah. Okay. So this is a typical flow chart of my fuzzer. So basically, it gets handled from device context. It gets handled for device, for context, and then it calls escape, which is like IOCTL for video. And talking about like how arguments and buffer goes to vendor-specific driver, when you like send some data, DXG kernel allocates that in a pool or in a stack. So basically, there are no time of check to time of use. Well, as far as I know, at the moment. Time of check to time of use vulnerabilities in the DXG kernel were found by Matthew Yurchik, aka Euro, and he found just 2, and Ilya Van Sprundel found 1. So I believe that right now in Windows 10, DXG kernel is kind of vulnerability bulletproof. So, but on the other hand, if user mode attacker cannot like change address, cannot use the race condition, DXG kernel doesn't know internal structure of proprietary vendor-specific buffer. So these checks have to be done by programmers of NVIDIA, ATI, and Intel. So, and there are like, they made the mistakes there. So, talking about reverse engineering, I don't have slides like how installation of video driver happens. Basically, it's an array of function pointers, and in initialization, basically, it's installed like callbacks. And one callback is escape. So in escape, the main argument is p-private data, which is just a buffer, and it's proprietary. So for example, for NVIDIA, it has to be this structure. So first the word has to be NVDA, then third word has to be 1, and Centra. So there is some structure. So it looks like I reverse engineer. So the first it's like D word and NVDA. I don't know like what means like second D word. There is third D word. There is private driver data size, then escape action, and then escape function ID. And escape function ID is actually the main point. The main thing is ID of like command, and after that, it's just a buffer of data. So talking about D word, the magic D word. On this slide is just NVDA, but in fact there are more code, so there are more like magic D words. I believe that it's just a different functionality. For example, NVGL, I believe that it's escape function codes related to OpenGL. NVDX, it's DirectX. DA, don't have idea. And V star star, it's like all others. CP, also don't know. So this the main field in this structure is escape function ID. So I reverse engineered, and NVIDIA driver contains two major regions, which is like from 10000 to 1000 122, and from 7 and to 7 like 182. So if I calculate it in hex, like 300, so around 800 functions. So it's pretty a lot of code, and it's in kernel. Talking about ATI, it has a bit different structure. First, the word has to be 80. Then, second, the word it's like can be 10,000 hex or 10,002. Then it's function ID, which is escape function, like ISTL, and then a buffer of data. And in ATI, it's kind of weird. So they don't like increment ID. They increment like a second byte in ID. You see, so basically it goes like in a second byte. Yes. So if you go and reverse engineer these functions, they like it's like a huge switch, right? So on the left, it's I believe it's NVIDIA, and on the right it's ATI. So you can see that like graph, it's kind of huge, right? So, and as we know that complexity kills security. So by fuzzing, we just need get handles to have ability to send escape data. So basically there is a structure which is driver info. There is handle to device context, handle to adapter, handle to device, and the handle of context. And the typical code to like start fuzzing, basically we get device context from desktop. Then we associate like context with adapter. Then we get context, and at that moment we initialize driver info, and we can start fuzz. Basically, we can invoke DXG escape function. So, okay. Oh, wait. Yeah, I just ran fuzzer here, but the problem is with video cards that I made research mostly on laptops, and this is PC, and chipsets, they're different, and it seems that driver and structure of this buffer is different. So for example, here my fuzzer is running, there is no blue screen yet, so I'm gonna show you just a video demo. So this is laptop with NVIDIA video card. Sorry, it seems that I was drunk, so well. Okay, I can ruin. So as you can see, there are like some output, iteration number, escape function ID, and sizes. I can fast forward. Yeah, so as you can see here, it's page fault, so it's 50. But if you see other parameters, it's second argument is 1, so it means that page fault happens on write, but unfortunately it's 0005, so it's null pointer dereference, so it's not that interesting vulnerability at the moment. So, yep, but I'm gonna like drop more interesting vulnerabilities. So in escape ID like 70094, my fuzzer triggered null pointer dereference, but it's not read or write, it's actually call. So basically, you can hijack execution flow. The thing is that on 64-bit operating system, it's not exploitable because you cannot allocate memory at 0 address anymore. But on 32 bits, till Windows 8, it's exploitable. So you can make a screenshot of offset and get the 0. So to show like complexity, right? It's just a stack trace of this blue screen. So do we have? This is laser, no? Ah, yeah. So this one, it's a system calling GDI32DLL. This is entry in kernel. This is Win32K. This is DXG, and this is stack trace of NVIDIA kernel driver. So as you can see, like nesting is pretty like 1, 2, 3, 4, 5. Like at the 9 level, it crashed. So I just I'm showing you that stack trace to like see that, to show you that complexity of video kernel drivers is pretty high. For example, size of NVIDIA kernel driver is about around 15 megabytes. So imagine like 15 megabytes of code in your kernel, and quality of that code is not very good. Another escape ID, it's as I can recall, it's out of bounds write. So it's a corruption of pool, basically heap overflow. And in fact, if you like go and reverse engineer like code of that function, you will see that that function is pretty funny, because in one function, it's rebooted. God damn it. Why you didn't make a video, huh? So, as you can see, like this information shows you that it's memory corruption, right? So we get out of some pool memory. But here you can see that in stack trace, stack is corrupted. And I remember I was reverse engineering that function, and in one function there are 3 vulnerabilities. There are 2 stack-based buffer overflows and 1 heap overflow in one function in 2015 in kernel. So yeah, because I cannot like tell what is a vendor, well, like responsible disclosure, blah blah blah. So it's like anonymous vendor. So you don't know which NVIDIA ATI, but it's just like statistics to show that in fact there is no quality assurance in these companies, you know? Because basically my fuzzer, it's nothing else, just a random generator. And the random generator, like basic fuzzer, triggered 17 null pointer dereference, 4 out of bounds writes, 4 stack overflows, NPD writes, execution flows, and like 2 unknowns. Well, there are actually APC mismatch, only blue screen. So yeah, like if there are developers of video kernel drivers, I suggestion, like recommendation is to, if you use pointers in this buffer, like use probe for read, probe for write, but fortunately, as you can see on this slide, right, there is no write-aware vulnerabilities. So before I started to research this area, I thought that I'm gonna find a lot of arbitrary memory overrides, but I was wrong. Why? Because if we go back and see structure, so it's in fact it's flat. So in all escape function IDs, this buffer is just array or some like data. There are no pointers. So good thing that developers in NVIDIA and ATI, they don't use pointers in like structures. So, yep, and like the recommendation also check like indexes, because one of vulnerability they don't check index, and they use it without any constraint checking, and it leads to memory corruption. But it's all about escape, which is kind of like AK IOCTL. There is very interesting system call which is called rendering, and the interesting thing about this attack vector that buffer that goes like to rendering, it's actually stream of GPU instructions. Why it's interesting? Because it like GPU, like hardware, basically processes it. So in theory, there are vulnerabilities in hardware that covers like chipsets, like not just like code, like I mean like kernel mode driver, but hardware. But the problem with vulnerability discovery and reverse engineering in this attack vector, because this GPU assembly is not, there is no documentation. Plus, it's very strict. So, for example, there is a stream of assembly instruction, and it has to be one opcode. Right after this opcode, another. So, blind fuzzing is, well, you're not gonna find any 0 days. Well, I believe, because I tried and I haven't found any. And the very interesting thing with rendering and with well, like reverse engineering and vulnerability discovery and this vector in GPU instructions, because it's not just for Windows. So yeah, basically what it does, so for example, it's how like to render shaders, how to like make some lightings. Also the instruction, they can make programming for paging, for context management, for even for execution flows. So, and as I told, it's not just about Windows. Very interesting vulnerability was found in Android for Qualcomm driver, and basically the mistake, the vulnerability was that they didn't set that one command is privileged. And using that command, you can basically have write like arbitrary memory override primitive. So that attack vector, actually, I'm gonna continue research of fuzzing and reverse engineering GPU instructions, because in the end you can get like ultimate exploit. It will depend on GPU chipset, but it will work in Android, iOS, OS X, Microsoft Windows. So it's pretty cool area. But the complexity that you don't know semantics of that GPU assembly, that is like hard thing. So yeah, that's it. I wanna say big thanks to Rodrigo Axel Monroy, which is my ex-coworker, and Rodrigo Branco, aka BS Demon. They put really a lot of effort to make that talk happen. So I'm gonna release like publicate fuzzer in end of November after Zero Night, so in the beginning of December. But if you wanna collaborate with me, you just drop me a tweet or just come to me and ask my email, because I think that we should basically make it public, because there are a lot of chipsets, a lot of versions of video drivers, and we're all vulnerable. Because I made this research, I think, in January of this year, and I was shocked that in 2015, I realized that huge amount of like privileged code is like quality of that code is horrible. And well, in Google Chrome you cannot use that attack vector, but in IE you can use escape. So it's not just privilege escalation, it's sandbox escape. And unfortunately, huge amount, millions and millions of computers, they are vulnerable as today. So I cannot say that like, for example, these two vulnerabilities are fixed, because I sent information like back in February, but like I haven't heard back from NVIDIA and ATI. If Axel Monroe is here, Axel is here? No? So they fixed? Or you don't know? They didn't respond. Yeah, well. So if community like attacks NVIDIA and ATI, probably we can change it, because I reported around 50 vulnerabilities. Like in total for NVIDIA and ATI, there are over 50. And I still don't know, like, are they fixed or not. So basically, let's show, can you like run again? Yeah, because this PC just rebooted. I just like, do you have like some camera to, like from for example, from cell phone to? Yeah, but it crashed like in a couple of minutes, right? Yeah, it took a couple of minutes. Yeah. So yeah, if you have any question, please ask.
¿Preguntas? Vean un grito, porque con la luz así no los veo si están levantando la mano. ¿Nadie? Sí, allá hay uno. Ahí voy.
Yes. Have you tried something in OpenGL?
No, haven't yet.
Okay. Do you think it's something interesting to?
Yes, it is.
Okay. Okay. Thanks.
Actually, this area is really huge, because imagine, like NVIDIA kernel driver is like 15 megabytes. So escape function, it's just one vector. Rendering is another. There is also OpenGL. So.
¿Otra pregunta? Y encima me conoce.
Don't be shy, come on, I don't bite.
Hi.
Yep.
Yeah.
Where are you?
Here. In the back.
Ah, okay.
Okay. Do you try something with PhysX of NVIDIA as a entry point?
Again? Sorry?
Do you try something with the PhysX
First.
of NVIDIA? The SDK of...
No, haven't tried.
Okay. No? It's maybe a possibility to, as an entry point, like this function of DirectX and OpenGL?
Probably, yeah.
Okay, thanks.
Yeah, I'm not going to leave the stage till this blue screen.
Mientras corra esto, podemos seguir haciendo preguntas.
Well, I can just drink water, right?
Si alguien le quiere preguntar en español, se lo traducimos también.
Yeah, so the thing is, I was kind of mad because I didn't expect that so so basic fuzzer gonna like makes such results. I thought that like at least they made fuzzing by themselves, but the reality that they didn't.